So up to this point, we've been working on differential rate laws, which are essentially concentration versus rate. And we did a whole bunch of stuff looking at experimental runs. Today, what we're going to look at is we're going to look at concentration versus time. And those are called integrated rate laws. And if you're a calculus fiend, then you'll be able to realize that you can integrate our differential rate laws to come up with our integrated rate laws. Now that's for a little bit later in case you want to get totally frightened, but let's take a look at our notes here for a second here. And I've defined these two things here for you, and if you take a look, the biggest thing here is that we're comparing, in this example, rate versus the concentration for differential, and here we're comparing concentration versus time. Now I want to take this equation right here, and this is a really blasé equation. A is our reactant, goes to 2B plus 3C. And I want to show you something because we've not included this portion right here. We've not seen this really written, and I wanted to comment on it so you aren't frightened. That is another way of saying rate, because rate is always the change in concentration of something over time. Now, there are three different things in this overall reaction. We have one reactant and we have two products. Now, what we can do, and we understand that all of our everything is going to be at the instant the reaction starts, right? So what we can do is we can say this. We know that the instant that this starts disappearing, A starts disappearing, doesn't B start appearing and C start appearing? So what they'll do sometimes is, instead of giving you the change in concentration over time, which is and you see how there's a negative sign in the front of that, that simply means that they're using the rate of A disappearing. But they could also make the rate be the rate of B appearing or of C appearing. Now what's really cool about this, and I want you to pay attention on this, is that because there's coefficients, we know this truth, that if we compare A disappearing, right, we're just going to put a little negative sign to mean it's disappearing, to B appearing, right, would you agree that double the amount of B appears for every A that disappears? Or triple the amount of C appears for every A that appears? And what that sets us up for is this. What they could do is they could give you a table, right? And the table has a bunch of concentrations. These are supposed to be square brackets, but I'm doing this fast. And over here they have a rate. And usually, if you look closely, it'll say something, and it'll be like the rate of the concentration of A over blah, blah, blah. What they could do is they could also say, if they gave you that data for A, they could say, well, what is the rate of appearance of B? And so if you know what your rate of disappearance is of A, you can look at your overall equation and see that B is going to appear twice as fast. Now, in the actual, if they do choose to write the rate in terms of B, they're not going to say 2A in there, because that's just the ratio between these two. But I want you to be familiar that rate and this are the same thing. So if you see it written like this, like change in C over change in T, which is change in concentration of products over change in time, that is what rate is. Now, if we took a look at this equation right here, and just to give you a practical example so we aren't using A, B's, and C's, if we took a look at this, we'd see that we only have product right here. And I'm telling you in this particular case that this is first order. We would not be able to write this rate law like this if we didn't know the order. Now, notice in all these other examples, I use the letter N. I don't know why I didn't do M. But that is what the order is. And we don't know what the order is, so we didn't write them here. But I'm telling you, based on some data that we got from a table, in advance, we know that this reaction right here is first order. Now, if that's the case, then typically what I've told you to write is rate is equal to K and K times N2O5. Now, we don't write the raised to the 1. And remember that this is a 1. The coefficient right here is never used unless we're dealing with elementary reaction, which is what we dealt with in the last video. I was trying to make that a little bit neater, but I just made it more of a mess. And also, if you notice here, since this is a reactant, the rate is the disappearance of N2O5. But do you realize they could have just easily written, instead of this, they could have written, oh yeah, the change in NO2 concentration over the change in time. And that would have been just as, give you the same exact results, except in this particular rate equation, if they actually did it in terms of NO2, because there's a 4 in front of this and there's a 2 here, NO2 will appear twice as fast as the N2O4. Or that kind of makes sense. Now, what I want to point out to you here, and I wish I hadn't made all these scribbles on this, but if I take a look at the actual equation itself above here, this rate law right here we can actually integrate it. Now, if you are a calculusy person, then you're going to feel really comfortable doing this. If you're not, this will not be comfortable, and we'll have to do some memorization. But if we take this, and we apply a process called integration, we end up with this. Now, I want to point out something to here. See that little zero as a subscript? That means initial amount. We call that naught. This is just this after having been integrated. Now, if you're frightened by this is why I had you memorize this table. But if you took a look at this actually is in the form of y equals mx plus b. And we're going to show you how this works with graphs, because one of the things that we can do is, instead of, by the way, using this equation, we're going to show, I'm going to make another arrow because that helps learning, evidently, sorry. We can take this equation, and if they give us an initial amount of N205, we can figure out the final amount as long as we know the amount of time. There's three variables in here: initial, concentration, and concentration, and this K is a constant, which we can find out from any sort of mathematics we do. But I want to go to graphs, because graphs will tell us what order our reaction is in as well, specifically when we're dealing with integrated rate laws. So here's what I'm going to show you here, and this is kind of a big deal. So whenever we want to know how long a reaction takes to reach a certain point, we can use graphs to do this. So whenever we're doing graphs, what you need to be aware of is that we're always going to put time on the x-axis, and whenever we're plotting graphs, we're going to plot three different things every single time until we get a straight line, because a straight line is going to indicate what type of reaction we have. And again, if this seems confusing, just hang in here with me. So on the first graph, we're going to compare the concentration of the reactant on the y-axis versus time. The second graph, we'll take the natural log, and that is ln, not log of n. That's really important. And then the last graph, we're going to plot the reciprocal. So what we're going to have is we're going to have a graph, and on the y-axis, we're always going to plot a different thing. On the x-axis, we're always going to have time. So we'll either plot the concentration of A over time, or we'll plot the natural log of A versus time, or we'll plot 1 over the concentration of A. That's what those words are there, which beg the question, how do we do that? Well, if we have data, we can actually figure out what the concentration of the natural log of concentration, or 1 over the concentration, is, and actually plot a graph. And our goal is to get a straight line, because depending on whether or not we have concentration, natural log of A, or 1 over A giving us a straight line, it'll tell us what type of reaction we have. Now, if that seems confusing, let's show you how this works. So, by the way, this is actually kind of helpful here. If you do a set of graphs in order, concentration, natural log, and reciprocal, it's alphabetical. And what that means is, if we get a concentration graph that is a straight line, it'll be 0 order. If we have a natural log line that gives us a straight, natural log graph that gives us a straight line, it'll be 1st order. And if we have a reciprocal concentration, which is this, giving a straight line, it'll be 2nd order. Again, sounds kind of confusing, so let's take a look. So these are the graphs that actually give us straight lines. So if we get do a concentration versus time graph, so this is concentration of A here versus time, and we get a straight line, we'll get a downward straight line, that's 0 order. If we were to plot the natural log of A for this 0 order reaction, or 1 over A, we would not get a straight line. We would get some sort of curvy line like this. Same thing, if we take a look, plot the natural log of the concentration of something versus time, we'll have a 1st order, and again, notice the slope is negative. And 2nd order, if we put 1 over the concentration, this is the same as 1 over concentration right here on the y-axis. We're using the phantom number A right here. This is natural log of A. We'll get a straight line. Everything else will give us curves. So they kind of say, oh, easily you can solve this from knowing, if you understand the time or concentration, you can use graphs to solve it. But this is actually a really, really helpful representation. These three right here, these are the integrated rate laws. Now, I asked you guys to memorize this. If you have not yet, you need to go ahead and do that. Or if you're really comfortable integrating, you can actually figure out from the differential rate, zero order, first order, and second orders, you can actually figure these things out. But what's cool about this is that if you set this up under the y equals mx plus b banner, you can actually understand what variables or what concentrations you find where. You notice here that our m is going to relate to our k, right? So also really important here, and I put this down below, the slope is always a positive. So if you're solving for k, we take the absolute value of that, because you can't have a negative value for your k, but you can have a negative slope because that just indicates direction. Now, again, this may seem a little confusing until we actually start doing this, but what we can actually do is this. We can actually write our differential rate laws like we did before. Rate is equal to k times the concentration of A based on which order we figured out. So if we plot the concentration of A versus time and we get a zero order, that means that down here we're going to write k a to the 0, which is just rate is equal to k. If we ended up with plotting natural log of A and that giving us a straight line, that would indicate first order, and that would give us k a to the 1. And similarly, if we got a 1 over concentration versus time and we got a straight line, we would end up with a second order. Now, how does this all play in? So let me take a look at the actual graph. So if we have a zero order graph, this is actually taken from data, and if you take a look, we have the concentration of A on the y-axis and we have time on the x-axis. And if you take a look, you see we have a straight line, and if we did not see that this was zero order, if we saw a line and it was concentration versus time and we got a straight line, that is always zero order. Now, just to show you, I did it backwards in the previous one. If we plot a natural log of concentration versus time for zero order, we get this looking graph right here, right? That clearly is not a straight line. So what we want to be aware of is this. The k, actual k value, is equal to the negative slope. So if we just had a graph, you know how we used to do rise over run? Like take any two parts, rise over run. We can actually do that to figure out what our slope is, and our k will always be the negative value of our slope. Yeah? So our differential rate law for zero order is just rate times k, and that's because if we take a and raise it to the 0, that's, 1. Now, again, if you are really comfortable dealing with integration, you can get from here to here, but if you haven't, this is what you need to memorize. This is the integrated rate law, and if you notice here, there are 4 variables that we care about. There's the concentration of A, there's the initial concentration of A, there's time, and there's a constant. So you realize if you're given 3 out of those 4 variables, you can solve for the 4th. So whenever they're giving you a problem, they're asking how long does it take for the concentration to go from 1 molar to 0.5 molar, and you give you a K somehow. They'd be giving us this information right here, this information right here, and this information right here, and wouldn't we be solving for T? Now, super fun fact, I've written this in this table so you can just have it later. A straight line is always going to be concentration versus time for a zero order, and the half-life equation is this right here. T1 half is equal to A naught over 2K. And this is important because it's another way we can identify a zero order is that the half-life, and by the way, I'm saying half-life without actually having taught you half-life. Half-life is the amount of time it takes to lose half of your original amount. So for zero order, it takes a certain amount of time to lose half the amount. But then the next half that you lose takes half that amount of time. And the next half takes half that amount of time. So the half-lives for zero order always get smaller by 0.5. Now, let's take a look at first order. Now, just to show you, if we had a reaction that was zero order and we tried to plot concentration versus time, do you see how we get a graph that is a curved graph? But if we plot natural log of concentration versus time, we get a straight line. And again, our k, which is we can pull from the actual graph, is equal to negative slope, or we could say the slope is negative k. This kind of doesn't really matter since we can manipulate this negative to one side or the other. But if you're ever trying to solve k for a reaction rate, we can actually look at a graph and do a rise over run like we talked about before and figure out the slope. A first order reaction, just so you're aware of it, the sum of all the rate law's exponents are 1. Although occasionally you can have two different reactants and they each are 0.5, but that is just crazy difficult. We're not going to pay attention to it. But let me just remind you what the differential rate law looks like. That's what we did before. The rate is equal to K times the concentration of A, and that would be A to the 1, but we don't really care about it. But you also should be aware of here, do you see how the rate is directly proportional to the concentration with the first order? So if the concentration goes down, the rate goes down. And that kind of makes sense because if you're losing concentration of something, the rate might slow down as well. When the concentration of A reaches half its original amount, we say that we've reached the half-life. Now, let's get into actually manipulating the equation. If I take this equation right here, this rate law equation, and I integrate it, I'm going to end up with this equation right here. Again, this is a must memorize equation. And again, it has the same 4 variables we had before, except you see we have concentration of A naught, that's initial concentration, and we have K and we have T. Unless you're really good at manipulating equations, I would suggest that anytime they're asking you to solve for something like T or K or any of these variables, unless they're actually going to solve for A or A naught, that you rearrange this equation and that this is the form that you use. Now, this may not look like it, but this and this, they are the same exact equation, and this is probably the best way to solve problems by using this. And again, you see the same time, K, our A, and our A naught. Now, if you want to math, and this is kind of super fun, if we go to half-life, isn't that the amount where we've lost half of the original amount that we have? So if our new concentration is half of what our original concentration is, wouldn't that be the same as saying 0.5 of our original concentration? So we can actually plug that into our equation, and when we put this 0.50 in here, down below, we actually get this. And this is a way that we can figure out the half-life for any equation. Now, this is also a big deal because if we're ever dealing with radioactive decay, that follows first order kinetics. And so here's what's a big deal on this. The curve for all first order reactions for a straight line is always the natural log of A on one axis and time on the other. Yeah, the slope is always going to be negative K, and let me just remind you, so I'm not a great drawer, but our slope will always look like this. But I also want to point out to you the half-lives, and this is the way we can tell it. If they give you, if you have a data table, and in that data table, you can see that each time that the time drops by, let's say this is our time, if our time drops by half and and we lose half of the amount, let me back that up. I misspoke there. If you take a look at this and you see that the time over a certain amount of time, let's say it's 48 minutes, and you lose half of it, then in another 48 minutes, you're going to lose another half. And only for first order do the amount of half-life, the amount of time it takes to reach each new half-life be the same. So if I had, let's say, 100, right? A concentration of 100, which is silly, right? To go to 50 minutes, or to 50, and then to 25, and then to 12.5, right? Each of these things that we're going to right here, the concentrations, each one would take the same amount of time. So if it took 5 minutes here, it's going to take 5 minutes here, and it's going to take 5 minutes here. Yeah, which is in converse to what we had for zero order, which each time the half-life would get shorter time-wise. Let's go to second order, and these are a lot weirder. You don't see these as much because this involves two things connecting, and this is the rate law that we're going to have to deal with, or this law right here, and this is our overall differential rate laws we wrote before. If you take this and you do some mathematical magic with integration, you're going to get this, and this is the equation you have to memorize. Now, this, I did not try and plot out the other two graphs right now, and this is what you can do on your calculators. Because remember, if you don't know what order you have and they just give you a bunch of data, right, in a table, what you'll do is you'll plot the concentration of A versus time, right? And you'll see what the graph looks like. So concentration of A, that's supposed to be an A, versus time. And if that graph is a straight line, then you're going to know you have a zero order. If you do the natural log of A versus time, and that's a straight line, that's first order. And here, if you do 1 over A, and you get a straight line, it's going to be second order. And notice here is the only graph that gives you a slope that's a straight line. Now, This equation you need to mess with here, and if we were to plug in 0.5 a naught right here for half-life, we could rearrange that equation, and this is the equation that we would get for our half-life. This, again, it's a weird thing, and I don't not seen this anywhere else, but this is another way you can determine what type of reaction you have. If you have the data and the half-life amount of time it takes to lose half of the original amount quadruples each time, you have a second order. Now, this table right here, let me just really this is the one you have to memorize. This stuff right here, and particularly this equation, and there's variations like for first order. Yes, you need to know this equation here. Unless you're really, really good at manipulating equations, I would memorize this equation right here as well, because that's going to allow you to solve problems a little more simply. Again, I will be giving you a quiz on this next class period, and I'm going to ask you to the information in this table specifically, because it's that important. Now, there is one more thing I need to hit on this before we close up here. What happens if we have an integrated rate law that has more than one reactant in it? And that's problematic, because let's say we have A times B squared, and let's just throw another one in here, C, and it goes to something else on the other side. Let's say, and let me do it this way. Let me actually make this as a rate law. Rate is equal to this. So let's say this is our rate law, right? And we actually want to know what's happening with our rate, like which of these things actually determines the rate. How do we combine all of them to determine what the rate is? When they give you a problem like that, usually what they'll do is they'll give you a lot of two of them. So they'll give you something like 1.0 molar of this and 1.0 molar of this, and they'll give you like 0.001 molar of C. And what that means is that if you're ever trying to do the mathematics on something like this, you can actually solve by only using the order for the one that you have the smallest amount of. So the way I wrote it here is that typically one of the reactants will start off with a much, much lower concentration. So our C in this example is much, much lower. So we can assume that that reactant's order will be the order of the entire reaction. Now that's because this. If I were to lose a little bit of A and a little bit of B, essentially I'm going to have almost exactly the same amount as I had before. But if I lose a little bit of C, that's going to shift the barometer of my reaction. They actually call this technique that we're doing, they call it swamping. So what they do is you put high concentration of all but one reactant and you perform an experiment. Again, you have to get the data from experiments, right? And if they see how they used even a smaller quantity for the one. And the rate is now dependent on the concentration of the little guys, since the big guys aren't really changing. And therefore, we could say the rate is equal to the K naught times the little guy. We call this a pseudo rate law, and the K is the pseudo rate constant. Again, this sounds really complicated. We can talk about this in class. Now, what I will show you, and I'm not going to go over this right now. You guys are probably experts on your calculators. I am not going to go through this, but I want you to, these are in your notes, I want you to walk through this. There's a video that looks like it's from the 80s, but it really is like 7 or 8 years ago. But it walks you through how to set up on your calculator graphs and how to do the graphs. And I want you to be able to do that. So if you want to watch this video, or if you already know how to do that, read through this, because whenever we're comparing, we're going to want to set up 3 different graphs each time. The first one, when you're doing your variables, it's always going to be time, and then you're going to have concentration, natural log of concentration, or reciprocal concentration. Those are going to be your 3 graphs. These ones right here. But again, I am not an expert. In fact, I just finally have gotten a TI Inspire that I'm learning on. So you guys could probably tell me how to do this better than I could, but you need a calculator at all times. Now, the other thing I want you to do is this. At the very bottom here, I put a bunch of practice examples. So I would like you to print out all this stuff by next class period. We will go over these, and that's by tomorrow. So even if you don't get to all of this video, which I guess you wouldn't be hearing me say this now anyway, you definitely need to print this stuff up. Anyway, I will go over this. If you have questions, I'm sure that you must have a ton, because I went through this pretty quickly. We'll go over these in depth in class. Hopefully it's been help. Have a blessed day.